So today we're going to talk about redox reactions. And so to define a redox reaction, it's going to be any reaction that involves a transfer of electrons between two atoms. So the atom or ion that's getting the electron or electrons is said to be reduced. And then the one that's losing electrons, we say is being oxidized. So a helpful mnemonic, or just two actual different mnemonics that you could use. Leo says GER, losing electrons is oxidation, gaining electrons is reduction, so that one can be helpful. Or oil rig, oxidation is losing, reduction is gaining. And both of those should make sense because if you're gaining electrons, you're becoming more negative, which means your oxidation number, which we'll talk about in just a second, is going down. So an example of an oxidation reaction would be combustion. You're pretty much always changing the oxidation numbers, oxidation states of several atoms when you have combustion. Another one would be the synthesis reaction. So you could also just call this an oxidation reaction because it's copper being oxidized by oxygen. This is how you get the green patina on, like, the Statue of Liberty. All right, so how do we know that a reaction is redox? And also what is being oxidized, what's being reduced. So the first thing we have to do, well, the main thing that we have to do is check oxidation numbers. And so oxidation numbers just sort of describe the distribution of electrons. And they can be thought of as sort of like charges. And in fact, when you have ions, the oxidation number is exactly the same as the charge. So I'm going to give you some rules here. If we have atoms in molecules, how do we tell what its oxidation number is? First of all, the easiest is for pure elements. Pure elements are just zero. So the chlorine atoms in Cl2, oxidation numbers on those two are just going to be zero. Fluorine is always going to be -1 when it's in compounds. Hydrogen is going to be +1 almost all the time. There are a few exceptions, like if you pair it with a metal, like a metal hydride, like sodium hydride. Hydrogen in this case would be -1. Oxygen is going to be -2, except the oxygens in peroxide, which is a polyatomic ion O2 with a 2- charge, where the oxidation number is going to be -1. Other halogens besides fluorine are going to be -1 unless they are paired with oxygen or fluorine, in which case the oxygen has to be -2 and the fluorine, or I should say the fluorine would have to be -1. And the last thing to keep in mind is oxidation numbers should add up to 0 for neutral compounds, and they should add up to the charge of a polyatomic ion. So let's take a look at some examples with those rules in mind. So we're just going to apply the rules, see if you can pause now and come up with the oxidation numbers for the sulfur and the fluorine in SF6. Okay, so I came up with +6 for sulfur and -1 for fluorine. Fluorine is always going to be -1, like we just said in our rules. And because there are 6 of them, that would give you a total negative oxidation number of -6. And because it's a molecule with no charge, we know it has to add up to 0, which means that sulfur would have to be +6. And since there's only one sulfur, its oxidation number is +6. So it's pretty much just like figuring out charges for ions when we learned how to write ionic formulas a long time ago. All right, let's go ahead and try it for H3PO4 as well as IO3-. Go ahead and pause and try those. Okay, so I went ahead and did 2 of the 3 atoms in phosphoric acid here, H3PO4, because I wanted to show you the logic here for phosphorus before I finish it out. We know it has to add up to 0. We know that oxygen is almost always -2. And so if this is -2 and there are 4 of them, that adds up to or multiplies out to -8. We know that hydrogen is +1 and there are 3 of them, so that's +3. So essentially we're just trying to figure out for phosphorus what sort of fills in the blank here, right? So +3, -8, and they have to add up to 0. So basically we need another +5, right? So I'm going to go ahead and say that phosphorus, and of course there's only one of them, so its oxidation number is positive 5. We'll go ahead and go through this iodate ion as well. It has a -1 charge, so we'll write that to start with. It also contains oxygen, which is pretty easy. It's always, or almost always, -2, but there are 3 of them, so that's -6. And so what number would complete the statement? Positive 5, right? So therefore, this is iodine. Normally iodine we would expect to be -1, but in this particular polyatomic ion, it's going to be positive 5. So that's how we assign oxidation numbers. Okay, so the next step, or the last step really, is to recognize if in fact we have a redox reaction, and then also what is being oxidized and what is being reduced. So let's go ahead and take a look at this first one together. We have iron and oxygen reacting to give us iron 3 oxide. We have elemental iron, which means it's not in a compound, which means its oxidation number is 0. And then elemental oxygen, so also 0. Okay. And then on the right side, we have iron oxide. So this is ionic. So all we have to do is pretty much look at the charges. Or we can make the oxidation numbers sort of add up to 0, which they should. So if I have -2 always on oxygen, or almost always I should say, and 3 of them, that gives me -6. And then +6 would have to be my positive oxidation number altogether. And if I divide it by 2, I get the oxidation number for iron on this thing is +3. So we can see here the iron is going from 0. So first of all, I should say it is a redox reaction because oxidation numbers are changing. And specifically, what's being oxidized, what's being reduced, the iron is going from 0 to +3. So it is being oxidized, right? And then the oxygen is going down from 0 to -2, so it is being reduced. All right, so see if you can assign oxidation numbers for this next equation. Go ahead and pause and do that. Okay, so here are my oxidation numbers I came up with. -3 for nitrogen and +1 for hydrogen in ammonia. And then we have 0 for elemental oxygen. And then in nitrogen monoxide, we have +2 for nitrogen, -2 for oxygen. And then in water, +1 for hydrogen, -2 for oxygen. And so then the other thing we can say is oxygen, which only shows up in one place on the left, but does show up in 2 places on the right. But either way, oxygen is going from 0 to -2, and then also have a -2 over here. So it is being reduced, right? It's going down in oxidation number. And then nitrogen is going from -3 up to +2. So this is definitely an oxidation, or a redox reaction, I should say. And we have our nitrogen being oxidized and our oxygen being reduced.